I hope at this point you have watched the YouTube video about scientific notation from Khan Academy. I'm going to run through the examples in your book so that you can see those done, and I'll explain as I go. Scientific notation is a way to talk about really big and really tiny numbers. The first example here is translating scientific notation to standard notation. Standard notation is a regular old number. So for example 1a, they have 3 and 1200ths times 10 to the 9th power. When you have a positive exponent, that tells you how many places to the right your decimal needs to move. So our answer here, let's see, 1, 2, 3. Always remember to drop your commas in, starting at the right every 3 digits. And here is our answer in standard form. So we have 3,120,000,000 here. B says 1 and 3500ths times 10 to the -4th. When you're talking about a negative number, that tells you how far left you're going to move that decimal. So we are going to have these, and then we start here and we go 1, 2, 3, 4 places. So your decimal is going to be there. And you need to fill in those egg cartons with zeros. So we end up with 135 millionths for this one. What I want you to remember, what's most important, is with a positive exponent, your decimal is going to go right. With positive, your decimal goes to the right. A negative, your decimal is going to go to the left. So that is essentially the key. Remember that with a positive number, you're talking about a really big number. With a negative number for your exponent, you're talking about a really little number. So if you see a negative exponent, you should see a decimal. If you see a positive exponent, you should not see a decimal, you should see a big number. So that'll help you to move back and forth between scientific notation and standard form with positive and negative exponents. The next example here is going from standard notation to scientific. So we, in example 2, are given 1, 2, 3, 4, 5, 6, 3 10 millionths. So there's 6 zeros and then a 3. And we are going to take that into scientific notation. The other thing to remind you is that scientific notation always has one non-zero digit before the decimal. So it can be between 1 or including 1, and it has to be less than 10. So it could be 1, 2, 3, 4, 5, 6, 7, 8, or 9 before your decimal. You can have a few digits after your decimal. You're always going to have that times 10 to some power. With a big number, it's a positive exponent, a little number, a negative exponent. So when we change this into scientific notation, we're moving the decimal right here behind the 3 because that's where we need it to land. So we simply count how many places did we move that decimal, and we moved it 7. It's going to be a -7 because we're talking about a really little number, a decimal. The next example is about monarch butterflies. So they say that a monarch butterfly has the average mass of half of a gram. So half of a gram for each butterfly. They're saying that there were 10 million butterflies in this colony in Mexico, and they want you to figure out what is their total mass in scientific notation. So we're taking half a gram and we're multiplying it by 10 million. So if we do that for every 0, we're moving this decimal place 1 spot. So we need to go 1, 2, 3, 4, 5, 7 spots. And we have 5 million now. So for 10 million butterflies, they weigh 5 million grams. And if we go to write that in scientific notation, it would be 5 times 10 to the 6th power grams. Still grams. So there you have it for example 3. There you go. There's one more example here, example 4, which is talking about blood cells. So in example 4, it says the major components of human blood are red blood cells, white blood cells, platelets, and plasma. A typical red blood cell has a diameter. So remember that diameter, if you have a circle, the diameter would be the whole way across. Radius is just halfway. Circumference is around that circle. So diameter is the entire way across the circle. Seem to have lost my eraser. Oh, there it is. Alright, so we're talking about the diameter. The diameter of a red blood cell, which is approximately 7 times 10 to the negative 6th meters. A typical platelet has a diameter of approximately 2 33/100 times 10 to the negative 6th meter, which has a greater diameter, a red blood cell or a platelet. So what we're doing is comparing these two numbers that are in scientific notation. Both of them happen to have the same exact exponent on their power of 10. So they're both 10 to the negative 6th power. What we can do in that case is go ahead and just compare these two numbers. 7 is larger, so this number is bigger than this number. If I want to write it this way, I can say, I think it was a red blood cell. So red blood cell is greater than platelet. There we go. So that red blood cell's diameter is greater than the platelet's diameter, and that is all we needed to do there. Again, if your power of 10 is the same, just compare this. If this is the same, just compare your power of 10. So let me give you an example like that. If we had, say, 3 23/100 times 10 to the 9th power, and 3 23/100 times 10 to the 7th power. My numbers here are the same, 3 23/100, so I can compare my exponents, and this would be bigger than this because my exponent of 9 is bigger than my exponent of 7. That's all I have for these examples. What I want you guys to do is the independent practice on page 177. And it is 11 to 20 all. I'll do a review for that and post it so that you have it. And I will see you then again with lesson 4-5. Take care.